Okay, so today we're just going to, I guess, review for some people or introduce for the first time homology with twisted coefficients. So I'll say what twisted coefficients are and then use that to define when a manifold is orientable. And then we'll talk about a way of thinking about twisted coefficients in terms of group rings. And then we'll talk about homology with twisted coefficients. And then we'll state a version of Poincare duality that works for manifolds that are potentially non-orientable. So that's the plan. And then, once we have a version of Poincare duality or once we have a statement for non-orientable manifolds, we'll use sort of these configuration space ideas to prove it next Tuesday. But just the point of today is to get a statement. Okay. Yeah. So what we know so far is that the homology of a space X is isomorphic to the homotopy groups, the free abelian group on that space, and the n minus ith cohomology is the ith homotopy group of maps into an island Broom-MacLean space. And yeah, so what did I write? Oh yeah, so we want to prove that if M is compact, then the free abelian group on M is homotopy equivalent to maps from M into the free abelian group on a cube mod its boundary, which then when you take homotopy groups will imply Poincare duality. And so it's going to be easier to prove if we, well, I guess I've not, in this class, I've not defined what orientable means. So we're definitely going to need know what that means in order to prove the theorem. And in fact, it'll be easier to prove if we have a version of the theorem that applies to for non-orientable manifolds. So the main goal for today is to just state what Poincare duality means for non-orientable manifolds. So let's just recall what a fiber bundle is. So a fiber bundle is it's a map of spaces such that the base B has an open cover, such that all the pre-images look like open set in the base cross some fixed set F, which is the fiber. And what does it mean that it looks like that? Well, we have this homeomorphism, and this homeomorphism is, I guess, like a fiber-wise map. So that means, it commutes with the obvious projection. Or, so that this map, the pre-image of the open set in B has a pre-image of that has a map to the open set, and then we say there must be a homeomorphism, and to the open set cross the fiber, and that comes with a projection, and this comes with a projection to the open set, and we just insist that the diagram commutes. Okay, so now I'll tell you what a bundle of groups is. Probably I should just tell you what a bundle with structure group is, but I'm delaying that. Okay, so so one warning. So for people who know what principal bundles are, that's another kind of bundle with fiber or group. This is a different kind of bundle. Okay, so we're going to fix a group G. It could be a topological group. It could be a discrete group. And then we're going to say that a map of spaces and so what's the data of a bundle of groups? So it's going to be a bundle, so it's going to be a map of spaces, and then it's also going to be for each fiber a choice of group structure. So this is called a bundle of groups with fiber G. If basically the same conditions before, so it's a fiber bundle, but now we have this extra condition that if you so this maps a homeomorphism, we require that on the fibers it's a group homomorphism. So, you can include, if you pick a B in this open set, you can include the fiber over B into the pre-image of the entire open set, and then there's a homeomorphism. The typo, I should have labeled the arrow with something else. By I sub alpha, maybe inverse. No, okay. Yeah, so and then that maps to U alpha cross G, and then you can just project onto G. So we picked a group structure here, and we picked a group structure there, and we just required that this composition is a group homomorphism. It's going to necessarily be a homeomorphism, so in particular, it'll be an isomorphism and respect all the topology. But just because we have a fiber bundle doesn't guarantee that this map is a group homomorphism. Any questions? Yeah, so intuitively you should just think of it as we have a fiber bundle, the fibers are groups, and the sort of fiber bundle respects the group structure, or the fiber bundle structure respects the group structure. Okay. So the main, or the most important example from the perspective of Poincare duality of one of these bundles of groups is the orientation bundle. And first I'm going to tell you what it is as a set, and then we'll describe what the topology is. So as a set, the orientation bundle is just the disjoint union over points in the manifold of the homology of the manifold rel in degree n, so m is an n manifold, rel the homology of m minus this point. And then there's a projection map from this set to m, where p of x is m if x is an element of this homology group. Oh yeah, someone joined. Were you having technical problems, or I guess it's fine if you're just late. Yeah. Okay. So this is a set. There's a map of sets, and then the fiber is clearly a group because, well, homology is a group. So yeah, my question is what group is this? Any takers? I claim that this group doesn't, up to isomorphism, this group doesn't depend on little m. So
it's just like the topology of a sphere.
Yeah. So which is Z. Yeah, I guess it's the top reduced homology of a sphere. So when M is a zero manifold, you get Z also. Whatever. That's probably not your point. Yeah. So okay. So yeah. So we're trying to figure out what is this group. So if M is an n manifold and we pick a point, then you can pick an open neighborhood. Pick some open neighborhood of M that's homeomorphic to R. That being a manifold means you locally look like Rn. So we can pick this neighborhood U that looks like Rn containing M. And excision tells us that the homology of M, rel M minus this point, is exactly is the same as the open set rel open set minus the point. And yeah, so what do we have? Well, this is the homology of Rn, rel Rn minus a point. But this pair, like Rn, rel Rn minus a point, is homotopy equivalent to, the pair is homotopy equivalent to disk rel sphere, which is just Z. Any questions on this computation? So if we go back, so this is a bundle, and all of the, or I guess we haven't said what the topology is, but this is a map of sets, and the preimage over every point in the base is a group isomorphic to Z. And so, this will turn out to be a bundle of groups, and I need to tell you what the topology is. So in the sort of group direction, like we're going to view this as discrete, or we're going to view the homology as discrete. So we have a bunch of Z's, and Z's are discrete. But the idea is that for, if you have M prime that's near M, then like they're some of the, I'll just say it's rigorous, or intuitively we want to say like homology in M, or homology of M, comma M minus M is near homology of M prime, or M comma M. There's too many M's for me to say this, but for nearby points, like these groups should have points that are near each other. Okay, so let's try to rigorously say what the topology is. So we have this manifold. We're gonna do is we're gonna pick open sets homeomorphic to Rn. We can M's a manifold. We can find a cover by these. And if you have M in here, the argument computing this, or maybe not that argument, but similar argument to the argument computing that this is Z, says that this is Z, and in fact that this map is an isomorphism. So both of these groups are Z, and so what does that give? That gives us a map from sets from U cross from U cross the homology of M rel M minus U to the disjoint union of M in U of this group. So in fact, like this map is a bijection, because what is this? Up to isomorphism, this is just U cross Z. And what is this? Well, this is a direct sum of M and U of Z's. So this map is a bijection, and we don't know how to topologize this space, right? But how can you topologize how can you topologize the thing that I just underlined in blue? With a topology that isn't the discrete topology. I'm trying to figure out a way of like asking the people who showed up late if they're having technical problems. But like they might actually have just been late, and I don't want to call people out for being late because I don't care. But like I want to know, email me if you had technical problems versus showed up, or if you just showed up late, I don't care. But if you had technical problems with WebEx, email me or tell.
I was just late.
Okay, that's fine. Yeah, I'm not trying to judge you. I just like actually, if there were, because last time we had technical problems, I just like want to know.
Yeah, Senator's late. Sorry.
Okay, yeah, no, I'm really like not trying to call people out. I just okay. Oh yeah. So my question is like, how do we, like, what's the topology on this space or set that's not the discrete topology? That's reasonably natural.
Product?
Yeah, just the product topology. Yeah, but this has a reasonable topology. Just view this as discrete. This is isomorphic to Z and view it as discrete. But then U has a natural topology, so just give this the product topology. And then we're basically just going to declare that this bijection is a homeomorphism, which will topologize this. Yeah, so what we do is we topologize this, the total space of O with the quotient topology coming from just like take the disjoint union of all of these, and then that's a overall U. You could pick your favorite open cover or just take all U homeomorphic to Rn in M. And so, this gives you a surjective map, and just topologize this with quotient topology, and that will tell you how to compare, when elements of different homology groups are nearby. So then this makes this whole thing into a bundle of abelian groups, or a bundle of groups where the fibers happen to be abelian groups. Okay. Yeah. So any questions on the construction of the, and this thing is called the orientation bundle. Any questions on the definition of the orientation bundle? Great. Okay. So I guess the definition of orientable is going to be that the orientation bundle is the trivial bundle. And so in order to define that, let me just tell you what it means for bundles to be trivial. So, well, what's a bundle isomorphism? A bundle isomorphism is a map of total spaces and a map of base spaces, making the obvious diagram commute. And a isomorphism of bundles of groups is, well, it's a bundle isomorphism such that on each fiber you get a group homomorphism. And so a bundle or a bundle of groups is called trivial if there's a, if it's isomorphic to a product bundle. And the isomorphism should, if it's a bundle of groups, it's called trivial as a bundle of groups if the isomorphism is an isomorphism of bundles of groups. And the jargon is a choice of isomorphisms called a trivialization. So you might have a bundle that's trivial, but there might be, non-equivalent trivializations. Being trivial means there exists a trivialization. And so a manifold is called orientable if this orientation bundle is trivial. So if you, what's the definition? So like, here's the definition of an orientation bundle. So being trivial means basically we can pick a continuously varying way of identifying each of these groups with Z. So each of these groups are isomorphic to Z, but we want to be able to pick such an isomorphism in a way that varies continuously. And so there's only one non-trivial automorphism of Z. So if I tell you a group is abstractly isomorphic to Z, but there isn't, necessarily a canonical isomorphism to Z, well, up to sign there's a canonical isomorphism because the only automorphisms are identity and multiplication by -1. So it's really like about picking like which of the two generators do you want to declare as one here. And if you've seen some more sort of differential geometric definition of orientation, it might have involved like basically picking some collection of vectors so you know what positive determinant means versus negative determinant, and you can think about that and figure out that that's equivalent to knowing which of the two generators here is the positive one and which one's the negative one. You know, or like if you like physics, it's like knowing what the right-hand rule is. You know, like if you live in a non-orientable manifold and you're taking a physics test, you know, and you're trying to compute some cross product, then you go to the bathroom, and then you come back from the bathroom using a different loop, you might come back and like using the wrong right-hand rule. Also, what's confusing is like for right-handed people, if you're taking a physics test, you're holding the pencil with your right hand, and you naturally want to use your left hand for the right-hand rule, and then it's hard to compute cross products. I don't know. Maybe I'm the only one who's experienced this. Okay. Sorry for that digression. Yeah, so a bundle is orientable if this orientation bundle is trivial. Great. So now we're going to talk about, oh yeah, so here's a sort of a reasonably, you know, in practice, often easy to check criteria for a manifold to be orientable. So, or for a compact manifold to be orientable. So a compact manifold is orientable if and only if the topology group is Z. If the manifold is not compact, then the topology is always 0. Okay, let's say, I forgot to say the manifold is connected here. Let's just assume the manifold's connected. Yeah. Well, yeah. If it's not connected, then you want Z to the like set of path components. And similarly, yeah. Okay. So yeah, so if the top homology is isomorphic to Z, the manifold's orientable. Yeah. One thing to say is, I guess, if the manifold is not orientable, there's some version. Well, let's say it's the interior of a compact manifold with boundary, then you want the homology of the manifold rel the boundary in degree n to be Z. Okay. So we'll do one direction of the proof now, and then the other direction we'll prove using Poincare duality. And then next time we'll prove Poincare duality. Okay, so let's assume that the top homology is Z, and then let's find a trivialization of this bundle. Well, our model for the trivial bundle is just M cross HNM. Like this group is isomorphic to Z. Doesn't depend on which point in M we're picking, so this is definitely trivial bundle. And you know, it comes with a projection map to M. So this is a trivial bundle. And then we want a map, we want a bundle isomorphism from this trivial bundle into the orientation bundle. And what do? Well, we just send M comma X to the image of, so HNM. You can check that this map is an ISO. Yeah, so yeah, you send MX to this group, you know, living in, oops, you know, this group is you know, is a fiber of the is one of the is the fiber over M in the orientation bundle, so it includes into the orientation bundle. Oh yeah, so bundle isomorphism, we need a map of total spaces and a map of base spaces, and you just take the identity on the base. And then this is an isomorphism from the trivial bundle to the orientation bundle, and so that's so the orientation bundle is trivial. And then later today we'll prove the converse using Poincare duality. Any questions? Great. Okay.
I have a quick question.
Oh, sure.
Is it in any way easier to compute the top homology to the other homologies, seen as they will be only cycles, right?
Oh yeah. So
like in general.
G, you're just computing a kernel, not a kernel mod boundary.
Exactly, that's my point. So in practice, when you actually want to compute it for manifolds, is it easier to do, or
I
are it
mean,
means that are better for it?
from the algebra perspective, at least, I mean, this is sort of tangential, but like computing kernels is hard and computing co-kernels is easy. I mean, depends what computing means. But like, at least from my perspective, if you give me an explicit chain complex, well, I don't know. Yeah, I mean, it might make things easier. I tend to think it's harder to compute kernels than co-kernels. At least, if your definition of compute is give a presentation, then something being a co-kernel just like automatically is a presentation. I guess like if you want to compute ranks, then you need to RREF matrices in either case. So maybe it's half the work then. Yeah, I was just more saying like this will tell you that like all CPNs are orientable. I guess like if you're viewing this as a computational tool, like hey, I already if you're like hey, I don't think necessarily you should think. I mean, sometimes you should think of Poincare duality as a computational tool, but at least what I think of it is just sort of it's a nice statement that like let's say you ignore torsion, you have a 20-dimensional manifold, the number of 2-dimensional holes and the number of 18-dimensional holes are the same. I just more think of it as like an aesthetic thing. I don't really think of it as like I have a 20-dimensional manifold. Oh great, I get to do half the work because I'll just compute the first 10 Betty numbers. Plus checking that it's orientable.
Right. Yeah. My idea was just like I was just curious as how easy, whether it was hard or easy to actually like in a concrete case check if something was orientable given this result. Like
this was more just like okay, so like I think if I told you prove CPN is orientable with the standard definition, it might be a little bit tricky. Right? Because you'd be like, okay, I need to like pick I have all these groups that are Z, but I need a way of sort of coherently saying what, maybe you should think of the orientation bundle as like around each point, you want to know what like the degree of a small sphere around that point is, like up to sign, or you want to know. Okay, yeah. So here's one way of thinking the orientation bundle. The fiber over a point is like look at a small sphere around that point, and you want given self maps of that sphere, you want to know what degree it means, not just up to sign, but you want to know like in absolute terms what degree means. So you want to know like what is a degree 1 map versus a degree -1 map, and you want to be able to pick that coherently, and it might not be obvious for a torus or CPN like how to make that choice, but then you can just compute the homology. Yeah, I mean it is true. Like if I gave you a cell structure, then you just have to compute a kernel. So it might be easier. And definitely there are examples. I mean, even like a reasonable amount of my research is sort of studying examples of spaces where like you're trying to compute the homology, and like in top degree it's easy and in low degrees it's easy, and in the middle it's sort of crazy. So that maybe these spaces aren't quite manifolds, but you know, it does happen in examples that, like, somehow the middle dimensional stuff is the most complicated. Usually.
Okay.
Yeah. Any other questions? Okay, yeah. So now I'm going to give like an alternate definition of bundles of abelian groups using the concept of group rings, and then that'll let us define homology with twisted coefficients. As I assume some people have seen group rings and some people haven't. Is there gallery view? I don't know how to. Whatever. I'll just remind people because some people might have seen it and forgotten. Okay, so basically the idea is if you have a group and a ring, you can build a ring. In fact, you only need a group and a monoid, but okay. So we have a group and a ring. Then as a set, the group ring is just R of G. Here I'm not thinking about topology, but obviously you could topologize everything, you know, if either of these objects had a topology. So, you know, what R of G as a set is just formal sums of elements in R times elements of G. And, you know, I guess it's clear how you add them. And the way you multiply things is via this formula. So yeah, so just you know, you multiply the elements in the ring and you multiply elements of the group. Okay. But yeah, and we don't need G to be commutative. We don't need R. I think we don't need R to be commutative. If I'm wrong, someone should tell me. Examples we care about G will be the fundamental group, so it definitely will often not be commutative, but R will just be Z usually, so R will be commutative in examples we care about. So yeah, so the proposition is that this structure makes R into a ring, or R of G into a ring. I guess it's, you know, if you want, you could say it's an R of G is an R algebra. You know, so in particular, this is an R module. Okay. Yeah, so that's sort of the first observation. So if people have taken representation theory, then sort of the first observation is that representations are the same thing as modules over the group ring. So yeah, so what do I mean by that? So let's say you pick an R of G module structure on Rn, extending the usual R module structure. Well, that's the same data as a map from G to GLNR. You know, and more generally, if you have an R module structure, typo, R module structure on an R module M, extending the, sorry, yeah, so if you have a group ring module structure on an R module, that's the same thing as group homomorphisms from G into automorphisms into M viewed as an R module. Yeah, so I guess why is that? Well, you know, what's a homomorphism? You know, what's a homomorphism from G into odd M? So this first proposition is the specialization of the second proposition. Okay, so a homomorphism from G into odd M is the same information as basically saying how does each element of G act on M? Well, if M is an R of G module, elements of G are elements of this ring, so then they act on M. That's the entire idea of this proposition. And you just, you know, write everything out and see that it's just exactly the same structure. So, you know, what this is saying is that modules over the group ring are the same thing as representations of the group. Any questions or things I should repeat? Okay. So why do we care about these? Well, so the theorem is that, so let's let X be a connected base space. Then there's a natural bijection between, modules over Z of the fundamental group and bundles of abelian groups over X. So by bundle of abelian group, I just mean bundles of groups where the fibers happen to be abelian groups. So it's saying that if you care about classifying up to isomorphism, bundles of abelian groups, that's the same thing as classifying Z of pi1 of X modules. And this isomorphism is natural if you pick a base point in X. And so if X is connected, then you shouldn't really think that that's a big deal. One sort of slight downside is I'll only be defining homology with twisted coefficients for base spaces, even though it does make sense for spaces that aren't based. Okay. Any questions? I'm not gonna prove this theorem, but I'm gonna say what the two maps are, and then the proof is just like you check that the two maps are inverses to each other. So I'm gonna tell you how to, given a bundle of abelian groups, build a module over the fundamental group, and given a module over the fundamental group, build a bundle of abelian groups. Okay. And then from this module perspective, it'll be a little bit easier to say what homology is. Okay. So I want to build a bundle out of a module. So X will be a connected base space, and X tilde will be the universal cover. Oh yeah, and so remember that pi1 acts on the universal cover. I think I decided that it acts on the right, but I'm not a precise enough person. If you think I flipped left and right everywhere, I'll believe you. And so we'll let M be a Z of pi1 module. So pi1 of X acts on M on the left. So we have this left Z of pi1 of X module, and pi1 of X is a subset of the ring, and the ring acts on the module, so the subset acts on the module. And the rings, and you might be like, okay, well, it needs to act as a group. Well, the way multiplication in the group ring works is it's exactly like multiplication in the group. Okay, so given all of this data, like the first 4 bullet points are just data, well, I guess, and general statements, I need to tell you how do you build a bundle of abelian groups. So we're going to let EM, so EM is going to be the total space of the bundle associated to M. So it's just going to be the quotient of the universal cover across M by pi1 acting on each factor. And I think I've picked the inverse so the actions work. So, in other words, I think the point of this is supposed to be that if we have X, if we think we're modding up an equivalence relation, it's like X G inverse comma M is supposed to be equivalent to X comma GM. Not 100% sure if this inverse. Maybe I don't want this inverse. Yeah. So this sort of equivalence relation is often written like cross over G M. And you could probably say it's like some pullback or fiber product or something. Okay, so given a module, we get this space. This space comes with a natural map. You just project onto M. This isn't a product bundle, but it's It's a quotient of a product bundle, and this projection is well defined. So, the theorem says that there's a bijection between isomorphism classes of modules and bundles, and sending a module to this bundle is one of the two bijections in the theorem. Any questions on this construction?
Is there like a similar bijection for like higher like homotopy groups, like Z of like pi n or of x?
I mean, I think what you probably want to say, yeah, because I guess you want to say like maps from X into B. I'm confused, but yeah, you should probably think of oh, you're saying that use like pi 2 of x? Or sorry, you're saying like Z of pi 2 of x?
Yeah, like
Yeah, I don't.
Yeah, I don't know if there's like maybe something like higher than that. I don't know.
Yeah, I'm slightly confused. I wanted to make some statement like you're aware of a statement like maps into classifying space, classify bundles. And like I feel like this is some like pi 0 of that statement. Yeah, I don't know. I mean, it is empirically true that in algebraic topology, Z of pi 2 of x modules never appears. So like there probably isn't a good statement just with that. But like there is, it's reasonable to ask. Like maybe your question is like, okay, instead of just like isomorphism classes of blah is the same thing as pi 0 of the moduli space of blah. And so maybe I want to know like what is pi 1 of the moduli space of blah instead of pi 0. And then there should be some nice statement about like what that is. And I'm just like blanking. Is that roughly what your question is?
Yeah, I was just wondering. Yeah, basically.
Yeah, I mean, it's slightly confusing because here, the usual statement is like bundles are classified by maps to the classifying space. But here we're like the fiber is changing, or somehow we're making that statement overall. Like Z of pi 1 of x modules is like all bundles of abelian groups. Usually you classify like things with a fixed fiber. But here we're classifying like lots of different kinds of fibers. Like the fiber could be Z or 0 or Z mod 2.
Yeah.
So you probably want to fix an isomorphism type of the fiber. And then, yeah. So if you wanted to fix an isomorphism type of the fiber, then it would be like Z of pi 1 of x module structures on M, where you fix an underlying abelian group structure on M, is the same thing as bundles of that fixed abelian group. And then you could use classifying space theory to say what that is, and then you'd want to say like, hey, the moduli space is just the entire mapping space, not just pi 0 or something. And then, yeah, I don't but yeah, I don't think like Z of pi 2 of x is going to, like Z of pi 2 of x modules, I don't think are going to be, is going to be what comes out, but like one could figure out what the correct statement is. Any other questions? Oh yeah. So maybe as a follow up on Zach's question, yeah, because you sort of maybe you want to think of pi1 of x as like it's like pi0 of the loop space. So, you know, if you wanted some topological statement, it would probably be like about representations of the loop space or something. I don't know. Yeah, any more concrete questions? Okay, so yeah, so this is how you build a bundle out of a module, and now I'm going to tell you how to build a module out of a bundle, and then we can check that the two maps are inverses to each other. Yeah, so this is going to use path lifting, and the next slide is path lifting. If I had a blackboard, you'd be able to see both at the same time. Great, okay. So we're going to start out with this connected base space, and we're going to start out with a bundle of abelian groups, and now we want to build a module over the fundamental group. So what are we going to do? Well, let's look at the fiber over the base point. So that's some abelian group A. We'll call it A. You know, so that's the fiber over the base point. And then a z of pi1 of x module structure on A is the same thing as a representation of pi1 of x. So we want to map from pi1 of x to the set of, you know, z module automorphisms of A. So the same thing as abelian group automorphisms of A. Just, you know, quick reminder, abelian groups and z modules are the same thing. Okay, so so I need to tell you, how does an element of the fundamental group act on the fiber? And this is something that should be familiar in from 571. So we have, you know, let's say we have an element of a fundamental group, view it as a path. And then I want to tell you how the element of the fundamental group acts on A. Well, an element of A is an element of the fiber, so we can view that as a lift of the base point. This is supposed to be lowercase a, or maybe A in capital A, which is written. Yeah, and then so you know, path lifting or unique path lifting says we can lift this path in the base to a lift in the total space, and it's unique. And then you just evaluate, you know, then we declare that F acting on A, I think I wanted to write equivalence class of F instead of equivalence class of A, is just going to be no way to fix that typo in a way that makes it more understandable. It's just going to be the lift evaluated at 1. So yeah, so what is this construction? This is just the usual way the fundamental group acts on a cover. So what am I saying? I'm saying we got this bundle of abelian groups. We want to, and we look at the fiber. Well, the fundamental group, you know, acts sort of in a fiber preserving way on any covering space. So it'll, you know, act on the fiber, and that gives you your module. Yeah, so this structure gives A a natural Z of pi1 of x module structure. One comment is that, you know, here group means discrete group, so a bundle of discrete groups is the, you know, is a covering space because the fibers all have the discrete topology. Great, so this is how you go back and forth between a module over the group ring of a fundamental group and a you know, equivalently a representation of the fundamental group and a bundle of abelian groups. Any questions? Okay. And there's a way of doing this without picking base points. And if your space is not connected, you can pick base points in every path component. Great. Oh yeah, and in case you forgot, this is lifting is so we have the element of the we're applying it to the case where f is an element of the fundamental group, so it's a loop. And then we pick, the loop is supposed to act on the fiber, so we pick here x is the point. We pick so to get a lift of the loop, we pick a point in the fiber. So that's just our point in A. And then we get this path in the total space. F is a loop, but F tilde is not a loop. And then we just see where the other endpoint of F tilde is. And that's how the fundamental group acts on the fiber over the base point. Okay, so now we can define homology with twisted coefficients. So, so let M be a Z of pi 1 of X module, equivalently a bundle of abelian groups. So the, and again, we'll assume everything's connected and depend on a base point because I'm being lazy, but you can work a little bit harder and show that, come up with a definition that's just functorial in spaces, not base spaces. So what's the definition? So the homology of X with coefficients in M. What do? We take chains on the universal cover, and you take M. Both of these are Z of pi 1 of X modules because pi 1 of X acts on the universal cover, so it acts on chains. So we can just take a tensor product over the group ring because they're both group ring modules. And then this whole thing is a chain complex, and then you just take the homology of that, and that's homology with twisted coefficients. Similarly, I don't know if I've written it anywhere, define cohomology, same thing, but just, I think I've written it somewhere. Cohomology of this. Okay, so here's an example. So let's say that, let's let pi 1 of X act trivially on Z. So in that case, trivial means acts as the identity, not as acts as 0. So that makes Z into a Z of pi 1 of X module. Well, this tensor product is exactly chains on X. Because what it does is it maybe I should just say that, like, let's let G act on some space Y. Then chains on Y, tensor over the group ring with the Z with a trivial G action. This is the same thing as chains on Y mod G. Okay, let's see. I don't know how to draw. Maybe there's like a subdivision argument. Let's say that G acts freely on Y, just for the and so the quotient of the universal cover by the fundamental group is just your original space. So so what's the upshot of this is homology with coefficients in Z is what we mean by this is a joke. Homology with coefficients in Z is isomorphic to homology with coefficients in Z. What do I mean by that? I mean homology with coefficients in Z viewed as a pi 1 of X module with trivial action is the same thing as homology with coefficients in Z viewing Z as just an abelian group as opposed to a module over the group ring. So I think Oh yeah, I want to kill one of these arrows. I think this is not an isomorphism. I think it's an equivalence. You probably want, you know, like when you're proving Meyer-Vietoris, you do some argument where you say we can chains on our space is equivalent, you know, to chains sort of subordinate to the cover. You'd probably want to do an argument like that to prove this. You'd want to first say maybe that's equivalent to chains that like pick some pick an, you know, if you pick an open cover here such that the pre-image, you know, you pick an open cover such that the pre-images look like products, well then replace chains on X with chains on X subordinate to that open cover, and same thing here except with the pre-image, and then it becomes, then those two chain complexes become isomorphic, and then that's how you show the homology is the same. Okay, so you know the upshot is homology, usual homology with untwisted coefficients is an example of homology with twisted coefficients where the action is trivial. Any questions? Okay. What is this? Okay. And we can define cohomology with twisted coefficients either just as the, you could take cochains, or you could take, which is the same thing as just hom from chains into the module. Yeah, so this is what homology with twisted coefficients, homology and cohomology with twisted coefficients means. And then, you know, the statement of Poincare duality, let's say for compact manifolds, is that the homology of M with coefficients in O is the same thing as the cohomology with untwisted coefficients. And similarly, homology is cohomology with twisted coefficients and the shift. So you can put the O on either side. And then when M is orientable, O is a trivial bundle. So then homology with twisted coefficients becomes regular homology, and cohomology with twisted coefficients becomes regular cohomology. So these two statements become the same statement and are just the statement that HI of M, or ith homology is isomorphic to N minus ith cohomology. Okay.
Go back to the previous slide just for 10, 15 seconds.
Oh yeah, sure. If you have questions also, but if you just want to look at it or write something down, that's... Everyone is aware all the slides are on my website, hopefully. I tried to upload it before class.
I don't think these slides are up.
Really?
For today.
Oh, okay. I'll double check.
Yeah.
I like today. I just was like, oh, I'll just like upload, because I tried to be a little bit ahead. So I upload last night. I uploaded like three. I thought I uploaded like 3 slides. Maybe I uploaded 2 slides, like all of next week's class, but not today. But I'll definitely upload it again and fix any typos that I remember.
Okay, you can carry on. Thank you for going back for a bit.
Yeah. So you know, this is, so using twisted coefficients, we get a statement for non-orientable manifolds. You just have to take homology with twisted coefficients. You know, in general, homology with twisted coefficients is kind of hard to compute, but it's nice to at least have a version that works for non-orientable manifolds. Oh yeah, so a while ago we said that a manifold has Hn isomorphic to Z if and only if M is orientable. And we proved one of the directions, and the other direction is just, well, if M is orientable, meaning the orientation bundle is trivial, then HIM is just, with coefficients in O, is the same thing as just homology. So if we're assuming Poincare duality, then we get homology of M with coefficients in O is n minus I cohomology for all I, and now you set n equals I. So you get, this is supposed to be an M. So the nth homology of M is the same thing as the nth homology of M with twisted coefficients, which is the 0th cohomology of M, which is just isomorphic to Z, because all of these theorems need the assumption that M is path connected, which I've forgotten. I'll try to add that to the slides. Yeah, so when M is path connected, Poincare duality implies that the top homology is isomorphic to the bottom cohomology, which is just Z. And if M is not path connected, then this would just be free abelian group on the set of path components, and that would tell you what the top homology is. Okay. Great. Oh yeah, so we're gonna prove this by showing that like spaces are homotopy equivalent. So our model for cohomology is saying that the n minus ith cohomology of with coefficients in A is just pi I of maps from X into an Eilenberg plane space. So we want a version for twisted coefficients. So let's say M is a Z of pi 1 of X module, then or equivalently a bundle of abelian groups. Then what space do we put here to get twisted cohomology? And the answer is you replace a mapping space with a section space, which is sort of like a twisted mapping space. So let me remind people what a section of a bundle is. So so what P from E to B be a map. I guess I'm usually going to think it's a bundle, or maybe a vibration. Probably always a bundle. So then the space of sections is the set of maps from, this is backwards, X into E. Maybe I should have called XB. Yeah, so it's a set of, sigma that go like this. Take points in X and output E, such that when you start out in X, take sigma to E, then you project back to X, you end up where you started. So it's a set of maps. It's a set of maps from X into E, such that when you project back, you get the identity on X. And just topologize this with the subspace topology. So this generalizes mapping spaces. So if your map pi is just projection onto X, then sections of this trivial bundle is the same thing as maps into the fiber. Any questions? If you just check like what is this data, the data X. We got E, and E, let's say E locally looks like a product. And what's a section? The light blue is a section. The purple is not a section. Okay, and so if your bundle is trivial, then the section space is just a mapping space. But if your bundle is non-trivial, then what you should think of it as is the space of sections is like the space of maps from X into the fiber, but the fiber gets to twist around your manifold. Okay, so Harry Ball theorem, this typo. So the Hairy Ball theorem says if there's no way to, you imagine you have this two sphere and it's got hair everywhere. There's no way to comb the hair so that there's no like bald spot or something. So what does it rigorously say? Rigorously, so we have this unit tangent bundle, which is you've the correct definition. Yeah, so it's the set of points in the set of pairs of unit length vectors that are orthogonal to each other. And then you can just, living in R3 cross R3, and you can just project onto, you forget one of the two. I could have done the non-zero one, but so we got this sphere, and what we're saying is at each point we have a fiber bundle where it's the set of all unit length vectors. And the Hairy Ball theorem, which I don't know if Ralph covered, but often as a 572 topic, says that there's this bundle has no sections, so the section space is empty. So definitely like maps from S2 into S1 is not the empty set. Easy to just take a constant map, for example. So in particular, this bundle can't be trivial because this bundle has no sections, but the trivial bundle does have sections. Okay. This is just a digression to at least relate this to something you may or may not have seen. Did Ralph cover the Hairy Ball theorem?
Not that I recall. No.
Okay. It's in Hatcher, but Ralph uses Muncrease. I don't know if it's in Muncrease. Okay. So, so what's space level cohomology with twisted coefficients? Yeah, so the idea is that if you have a fiber bundle, then you can build a bundle of abelian groups out of it whose fibers, so let's say E is a bundle. We're going to build a new bundle called pi NE. Maybe this is a little bit misleading because I don't literally mean pi NE. I mean a bundle whose name is this. Maybe I should have given it a different name. I made up this name. Now I realize it's a bad name. This is the name of the bundle. I'm not saying literally take pi n of E. And the fibers over B are sort of naturally given by pi n of the fibers. Oh, better name would be pi NP. Not a great name. It's a better name. I don't know. And so the analogous theorem is that the analogous theorem to saying the homotopy groups of mapping spaces in Dieterle-Bergman-MacLane spaces are cohomology is saying that if you have a bundle whose fibers are all Dieterle-Bergman-MacLane spaces, then the homotopy groups of the section space is the homology, but now with twisted coefficients. Decided to rename this INP. Yeah, so what I'm saying is if you have a bundle of Dieterle-Bergman-MacLane spaces, then the homotopy groups of the space of sections of that bundle are the homology, but now with twisted coefficients. So section spaces are like twisted mapping spaces, and twisted coefficients are like regular coefficients but twisted. So you sort of have, for each point in B, we have this group that maybe is isomorphic to A, but non-canonically, and the section space, we over each point, we get like each point in B, we're mapping it to some space that's non-canonically isomorphic to F. Yeah, so we're just sort of twisting both sides, and then yeah, so you plug in everything as trivial. This gives you the theorem we proved last time. And you can prove this theorem with the same proof that we used in the untwisted case. Okay, so what we're going to do next time is we're going to find a bundle whose name is going to be KON. I'm going to give it a different name next time, but yeah, so we're going to find a bundle of Eilenberg-MacLane spaces such that when you take pi n of a fiber, it's naturally a fiber of the orientation bundle. And then we're going to construct a homotopy equivalence from the free abelian group on M into a space of sections of this bundle. And then, the homotopy groups of this are going to be the homology of M. The homotopy groups of this are going to be homology of M with twisted coefficients. And then that'll prove Poincare duality. And then you specialize the case where the manifold is orientable, and you're going to get, the statement with untwisted coefficients.